Good morning. This is Mr. Waters, and I hope that you and your families are feeling well this morning. Everyone is safe. We're going to continue here from Waters Studios about the fundamental theorem of calculus. Today, that's something called the fundamental theorem of calculus. It's our continuing series about calculating areas under curves, and specifically right now something called the definite integral. Okay? But what we're going to lead to today from definite integral, what we're going to head for is a definition of something called the fundamental theorem of calculus. Okay? It's one of the most important ideas in calculus. It and the concept of the definition of the derivative are the two pieces of calculus that make it all work and make it all fit together. Okay? So first off though, I want to talk about units a little bit. If you'll recall, when we worked with derivatives, we started with the idea of the slope formula, right? And we wrote that as delta y over delta x. And then through a limiting process, through the definition of a limit, we found out that the derivative, which was the rate of change, well, that was, dy over dx, where it was the same thing as delta y over delta x, except the deltas, the change in y over the change in x, were infinitesimally small. Okay? But as far as units go, the units, the rate of the derivative, what it measured was the rate of change of whatever y was with respect to x. So, so what we said for units here, for the derivative, we said, okay, if we've got, x here and we've got y there, then the units of the derivative, dy over dx, were the ratio, because this derivative was still a ratio of the change in y over the change in x, and so the derivative units were a ratio of the y units and the x units. So if this were, I don't know, it could be whatever you wanted. It could be centimeters, and this could be light years, right? It literally didn't matter. Then the units of the derivative would be light years per centimeter, okay? Or, just to pick another one here, this could be dollars, right? And this could be pounds. And then that would mean that the units of the derivative would be the rate of change, would be in terms of dollars per pound. The rate at which dollars changed in terms of pound. So dy dx in that case would be, the units would be dollars over pounds, like that, right? So that's something we worked with before. Well, the units for our integral are going to be kind of a similar way. When we worked with an integral, when we started first off with our simplest case of the rectangles, we started again with a simple formula, length times width, right? Which gave us the areas of each of our Riemann rectangles that we were adding together to get the Riemann sum, right? Well, here's the Riemann sum. We're taking a whole bunch of these and adding them where the height was f of x at a given point, and the width of the integral, we called it delta t, but in this case, we're just going to, instead of t, we're going to use x. So this was the height of each of the rectangles, and this was the width, delta x, of each of the rectangles, and we added together a whole bunch of them according to however many intervals we had designated, right? And that gave us the estimate of the area under the curve, right? Well, if we, again, through a limiting process, we let n go to infinity. We let n get larger and larger and larger and larger, which allowed x to get, or delta x to get smaller and smaller and smaller and smaller. And if we visualize delta x being infinitesimally small, the net as close to zero as close to zero as we can get without it actually being zero, we ended up with this definite integral here, right? Well, so what are the units? Well, you can see here, keep in mind, and I'll do this in purple, okay? Okay, there's A and there's B. This f of x dx is the area under the curve. Let's call it capital F, that designates that entire area. and then this little function there, the curve across the top, the equation across the top there that we're getting the area under, well, that's little f, right? And capital F, that was the area under the curve. Well, what are the units of that? Well, remember, going all the way back here, this is length times width, or x times y, right? And so, in the same way, we can designate the units of whatever the integral is. So, for example, if this was, I'll make another one here. This will be x and this will be y, right? And then here, and I'll draw this again. This is f, and this is a and b. I'll just draw another version of that so it's a little less busy. This is f. Well, what if the units are, I don't know, dollars and, well, actually, we started out with the units were speed and time, right? So what are the units here? The units of speed are, let's say, miles per hour, right? And over here, well, this was units of hours. Okay, well, you can see that the area units are going to be, to get the area units here would be, you know, length times width would be the y times the x, because we're multiplying the units here, y times x. So the units of the integral here, the units of f, the area under the curve will be the speed units, whatever they are, times the time units, right? Well, that was miles per hour, miles over hours, times hours, right? And that's really fraction-wise hours over 1. Maybe you can see that when we multiply, the hours cancel out, and the units of the area are miles, which is just what we'd expect, because the area under that curve was supposed to be the distance, wasn't it? Which would be measured in miles, right? Okay, see how that goes? Okay, or let's pick another one here. Okay, if this was use purple again here. Let's say the y units were units of force, newtons, right? And let's say that the x units were units of distance, meters. The area under that curve F would be the y units newtons times the x units meters, right? So the units that what were the area under that curve would be, the units would be, we would call them, and in physics you call them Newton meters, okay? Which is just the area under the curve, which is the measurement we get when we multiply force times distance, right? That's why the units for force times distance works out to be Newton meters. Okay, anyway, so that's how that goes. Okay, so we're going to stop this first little video right here. Well, actually, I'm going to do one example. Okay, so one thing you're going to want to be able to do is interpret, once you've got an integral, you're going to want to interpret what the units mean. Okay? Okay, so on this one here, I'm going to put that page aside here. I'm going to make up a little example for you, and you go ahead and try this, please. Okay, so let's say I've got let's say that I've got this curve right here, and the units are dollars, and that's the y units, and the x units are pounds. What would be, if we calculated the area under this dollars function here, right? So, you know, y is going to be equal to some dollars amount in terms of pounds. What would be the units under that, what would be the units of the area. Okay, so pause for a minute. Hit pause if you have to. Well, hopefully you can see that the units, okay, you're back. Okay, hopefully you can see that the units would be dollars times pounds, because it's length or width times length. Dollars times pounds, and we call them dollars pounds. How we would call that unit. Okay, all right. So that's enough for this first video. All right, the next one will have to do with the fundamental theorem of calculus. All right, bye.